Hey, geometry. Nope, I'm not there today. So you have a video lesson. We're talking about scaling just a little bit more. So first of all, going backwards. So the image shows a cone that has a base with an area of 36 pi square centimeters. It's a circle, so, oops, I don't have my pen out. Area is pi r squared. That's my dog snoring. The cone has been dilated using the top vertex as a center. That means it's going to be a symmetrical dilation. So the area of the dilated cone's base is 729 pi square centimeters. So what was the scale factor of dilation? So we're talking about area. So with area, we take our scale factor, which is k, and square it to get to our new, to get from our pre-image to our image. So we can say here that our pre-image is really 36 pi, and we're going to multiply that by some type of scale factor squared to get 729 pi. So let's go ahead and divide both sides by 63 pi. 36 pi, sorry. Sometimes I do that. It's very annoying. 729 divided by 36. K squared equals 20.25. I'm going to take the square root of both sides. And I get K as 4.5. And you can always test that out. 36 pi times 4.5 squared. Just leave the pi there for later. And I get 729 pi. The pi was just hanging out till the end. All right, we do have problem cards and data cards. Bad day for me to be gone, I know. And it just stinks. So I'm going to just read through them. Obviously, one person would have a problem card, one person would have a data card. So looking at the problem, a rectangular prism was dilated. Your partner has some information about the dimensions, surface area, and volume of the original and dilated prisms. Draw the original prism, labeling its height, width, and length. Let's see, the original prism's volume, we're going to just do a O for original. Volume equals 30 centimeters cubed. And then the dilated volume, let's see, is 240 centimeters cubed. So I'm going to find out that scale factor. 240 divided by 30. And its volume, so I'm going to take the cubed root, which is going to be 2. I've got a scale factor. Let's see, the length of the original prism, this is a rectangular prism, is going to be, the length of the original prism is 5 centimeters. Let's see, the height of the dilated prism is 4 centimeters. Whew, I'm not going to be able to draw. It's too late. You guys know I'm not there today because I'm working on a midterm for my college class. It's about 1:45 in the morning. I'm about halfway done, and I didn't get to record your lesson yet. So let's just do this. Original over here, and dilated over here. So the original length is 5 centimeters. That means my dilated length is going to be times 2. The height of the dilated is 4. So the height of the original I'm going to divide by 2. And then the original prism surface area and dilated prism surface area. These I should be able to do a 248 divide by 62 gives me 4, and that's a surface area, so I'm going to take the square root, and luckily my scale factor is the same. Height, width, and length. Let's see if a surface area, that's not going to be able to get it though. I know I can do volume equals length times width times height, where we know the length and the height, and we know the volume was, this is the bigger one, 240. So I'm going to take 240, divide by 10, divide by 4, and I get 6. So my width is going to be 6. So I'd have to draw a shape with these dimensions. Pretty sure I don't want to do that right now. It's not going to be pretty. For the original, my volume was 30. And that's going to be height times width times length in any order. That means my width is going to be divide by 2, divide by 5, 3. So I would have to draw something with these dimensions. That was sort of fun. Let's try it again. Problem card 2. Your cylinder was dilated. So we have a cylinder, right? I'm probably going to need that room, so I'm going to erase that. Let's figure some things out. So the original cylinder's surface area was 80 pi. The dilated surface area is 1280 pi. Let's go ahead and find our factor. So we went bigger. I'm going to go 1280 pi over 80 pi. That gives me 16. And this was surface area, so take the square root, that's my scale factor. So we did those. Let's see, the volume. Oh, I didn't read the instructions. Your partner, find the volume of the dilated cylinder. So the original cylinder is 75 pi. I need to multiply it by my scale factor cubed. That gives me 4,800 pi, not centimeters, meters. I can't read it. Let's see. Sorry, I didn't leave enough room. Meters cubed. That seems too easy. It didn't want me to do anything else. Nope, that's it. Good job. That was the easy one. All right, moving on. Jumbo Can. A beverage company manufactures and fills juice cans. They spend 4 cents on materials for each can and fill each can with 27 cents worth of juice. The marketing team wants to make a jumbo version of the can that's dilated. That's a dilated version of the original. They spend at most 16 cents on materials for the new can. There's no restriction on how much they can spend on the juice to fill each can. The team wants to make a new can as large as possible given their budget. By what factor will the height of the can increase? Explain your reasoning. That's very fun. These are kind of real-world problems. So we want to see how much we can expand. I'm going to use this information. I've got a 16 over 4. I'm just doing cents. That gives me 4. And that would be, materials would be surface area. So I'm going to take the square root of that. I think that means my scale factor is going to be 2. So when I'm talking materials, I'm really talking surface area. You guys probably didn't know that, and I didn't tell you. So I'm going to compare my surface area and figure out what the scale is going to be. My original is smaller. I'm trying to get bigger, so I take the bigger number and divide it by the smaller number, which gives me 4. And I'm talking area, so I take the square root of my scale of 4. Take the square root of 4 to get my scale factor. Yep. Yeah, I'm getting tired. So my scale factor is 2, and that was my reasoning. By what factor will the radius of the can increase? Oh, golly. Well, the radius, it'll just increase by 2. Yeah, because that's my scale factor, and the radius is a one-dimensional measurement. So the radius will increase by a scale factor of 2. Yeah, made total sense. Okay, let's move on to the next question. Create drawings of the original and jumbo cans. Okay, I can't wait to see your drawings when I come back on Monday. That's a really awesome drawing. I just know I want to go a scale factor of 2. Yeah. So if you just made your radius and made this radius, it would do well, right? I made this a height, and this would be a 2 times my height. That's a perfect drawing. That's exactly what I want to see right there. Cool. Number 4. What geometric solid do the cans resemble? A cylinder. Rocket science right there, folks. What are some possible differences between the geometric solid and the actual can? The actual can isn't going to have anything on the inside except juice, where the solid is going to be full of whatever you make it out of. We could 3D print it. It'd be full of filament. We could carve it out of wood, and it'd be full of wood. We can make it out of Play-Doh, right? That's a funny question. What will be the total cost for materials and juice? Fill for the jumbo can. Explain or show your reasoning. So, the fill cost is related to the volume of the can. The volume is going to scale by 2 to the 3rd power, which is a scale factor of 8. We know how much it costs to fill the original can. So the cost to fill the new can is going to be 27 cents times 8. Oh, my calculator turned off. Which is $2.16 of juice. The total cost to make and fill the can would be $2.16 plus 16 cents, which is your material cost. That'd be, I did not need a calculator for that. That's so funny. $2.32. Describe any other factors that might cause the total cost to be different from your answer. I guess, it's assuming that we can put the exact percentage of juice in to the original can and scaled up into the new can. The material for the new can might need to be thicker. Just because it's a bigger can, it has to hold some more juice, so you might need thicker walls. But we're just assuming there. That's all I got. Good job. I'll see you Monday.